In this lesson, you will learn and apply matrix terminology. Now the first term that we need to know is, what is a matrix? Well, a matrix is simply a rectangular array of numbers enclosed by brackets. So below we see several examples of matrices, where we have negative numbers, we have mixed numbers, we have fractions, we have radicals, we have negative decimals. We can have any sort of number inside of a matrix. And the plural of the word matrix is the word matrices. Now within a matrix, we have what we call elements, which is each number in the matrix. So the number 3 is an element, the 0 is an element, 9 is another element. All of the numbers are an element. And then we have rows, which are the horizontal components. So right here, going across, 3, 0, 9 would be one row, and then 0, -2, 0 would be another row. And then columns are the vertical component. So vertically, we have 3 and 0 would be one column, 0, -2 is another, and then 9, 0 is another column. And then we have what's called the dimensions of the matrix, which is essentially the size of the matrix. And the size is determined by the number of rows by the number of columns. So in this example, we have 2 rows. So we have 2 rows, and then we have 3 columns. So the size of this matrix would be 2 by 3. Now it's not 2 times 3. The x just means that we have 2 by 3. We have 2 rows by 3 columns. Now here we have 3 examples where we are trying to determine the dimensions of these matrices. So the first one, once again, we have 1, 2 rows, and then we have 1, 2, 3 columns. So the dimensions would be 2 by 3. The second example, we have 1, 2, 3 rows, then we have 1, 2 columns. So the dimensions would be rows by columns, which would be 3 times 2. In the third example, we have 1, 2, 3, 4 rows and 3 columns, so the dimensions would be 4 by 3. Now some other terms to know would be some examples of special matrices. The first one is a row matrix, which by definition has exactly one row. So for example, we see here this matrix only has one row. It can have multiple columns, but only one row. A column matrix has exactly one column, where here we see there's only one column, but there are 3 rows. So for the column matrix, it does not matter the number of rows as long as we have just one column. The next type of matrix is called a square matrix. Now we should know that a square has the same width as it does the height. But in the case of a matrix, same concept, we have the same number of rows and the same number of columns. So for example, we see here the first one has 2 rows and 2 columns. The second one has 3 rows and 3 columns. The number of rows and the number of columns are the same measure. Now when you're naming matrices, we can use capital letters to name them. So instead of writing out the matrix every time, we can use capital letters instead. So for example, we can call this matrix matrix A if we would like. And the dimensions of matrix A would be 2 rows by 3 columns, so it's a 2 by 3 matrix. And another way we can write this, instead of just using the letter A for the matrix, we could be more specific and say A and put the little 2 by 3 beneath it. So put the letter and then the dimensions underneath of the letter. Now another matrix we have is called a zero matrix, and it's just how it sounds, where it's a matrix where every number is a 0. So for example, this matrix has all zeros, so this would be a 0 matrix. Now when naming 0 matrices, we use the letter O to represent a 0 matrix, probably because an O looks just like a 0. And then being more specific, I can use the dimensions underneath the letter O, and this is a 3 by 3 matrix, So I can call this matrix O and then a little 3 by 3 underneath it. So the question might ask, how would a zero matrix with dimensions of 2 by 5 be written? Well, it'll be written as an O and then a little 2 by 5 underneath it. And the way it would look would be 2 rows by 5 columns. So something like this. Next, we need to discuss a topic called equal matrices. Now, equal matrices are matrices that are equal, meaning we need something along these lines where every corresponding element is the same. So the top left corner over here is a 1, top left over here is also a 1. Top right is a 2, the other top right is also a 2. So every number needs to be in the same location with the same size of matrix. Whereas this one here would not be equal because notice the 2 is not in the same place. We have a 2 here, but then a 3 on the top right instead. So because of that, this would not be equal matrix. Even though it's the same dimensions, even though all the numbers are the same, the numbers are not in the same corresponding location. Now, given the idea of equal matrices, let's say you're given 2 matrices like this that are equal, and your objective is to find the value of the different variables. Well, if they're equal, we know that the corresponding parts are going to be equal. So the x plus 5 would equal this 2, and the 6 would equal 3y. So I can set them equal to each other and then solve. So x plus 5 equals 2. I can solve for x by subtracting 5. So x would be 2 minus 5, or negative 3. And then to solve for y, I can set 6 equal to 3y, solve for y by dividing both sides by 3. So now I have y equals 6 over 3, which is going to be 2. Now, one last example. We see here that we have a 0, 3 by 2 matrix equaling this matrix over here. Well, this notation on the left side means we have a 0 matrix with 3 rows and 2 columns. So it looks like this. And if they're equal, then we can solve for x, y, and z because the corresponding parts will be equal. So to solve for y, y is in the top right corner, and then that's going to correspond with this top right corner. The x corresponds with that location, and the z corresponds with this 0. So notice every variable would have to be 0 because it's paired up with the 0 in the other matrix. So x is 0, y is 0, and z would also be 0. And that concludes our lesson for today. We will see you next time.